we can use what we've learned so far about matrices and their connection with systems of linear equations to produce a method which will solve any system of linear equations. And that method is, we put the equations into matrix form, we do row operations to the augmented matrix until it reaches some kind of simple form where we can easily read off the solutions, and then we know that the solutions to this new system are the same as the solutions of the original system because we showed that doing row operations doesn't change the solutions to our system of equations. The simple form that we're going to use is row-reduced echelon form because we know that we can put any matrix into row-reduced echelon form by doing row operations to it. What we don't yet know is how to get the solutions of a system of linear equations whose augmented matrix is in row-reduced echelon form. That's what we're going to investigate in this video. So let's suppose that we started with an augmented matrix and we did some row operations to that augmented matrix and we ended up with this row-reduced echelon form matrix as the augmented matrix of our new system. So this one just here. Let's find the solutions to this system. So this is an augmented matrix, which means that the last column corresponds to the right-hand sides of our systems of equations, and the other columns correspond to the variables. Let's give some names to those variables. So this one will be x, y, z, and the last one will be w. And the equations are then that x plus 2z is equal to 0, y plus 4z is equal to 0, w is equal to 0, and then the last equation would say 0 is equal to 1. That last equation is impossible, so there are no solutions to this system. In fact, in general, whenever your row-reduced echelon form matrix has got a leading entry in its last column, you're going to get an equation of the form 0 is equal to 1, and of course that's impossible, so your system will have no solutions. So let's change the right-hand sides of these equations to make it a more interesting example in which there would be some solutions. So I'm going to get rid of this last column and I'm going to replace it with 1, 2, 3, and then a 0, so we don't have this problem about 0 is equal to 1. So if I do that, nothing changes about the left-hand side of my equations, but the right-hand sides become 1, 2, 3, and then 0. And the last equation just says that 0 is equal to 0, so we might as well get rid of it, since that is always true. Okay, well, before we do anything else, let's think about these equations here. You can see that there's something special about the variable z, because for each of the other variables, we can simply rearrange this with no multiplication by constants to get an equation expressing it in terms of z. So this one would lead to x is equal to 1 minus 2z, and this one would lead to y is equal to 2 minus 4z, and this one, well, this one just says w is equal to 3. And the reason we get these equations is because the columns of our row-reduced echelon form matrix, which can correspond to x and z and x and y and w, contain leading entries, and those leading entries are 1s, so you get matrix equations which you can rearrange to say x is equal to something in terms of the variables on its right, so y and z and w, and then you'll get an equation that says y is equal to something in terms of the variables to the right of y, and so on. So we have a special name for these variables whose column has no leading entry. In this case, it's just the variable z. And those things are called free parameters because since there's no leading entry in that column, the values of the free parameters can be chosen freely, and then the other variables will be uniquely determined by those choices. So let's record that here. The value of z can be freely chosen. So I mean that you can make z equal to any number that you like. And then once you've made that choice, the other variables are uniquely determined. What I mean by that is if you choose z to be equal to 42, then x must be equal to 1 minus 2 times 42, and y must be equal to 2 minus 4 times 42, and w must be equal to 3. So in general, we can follow this procedure to solve any system whose augmented matrix is in row-reduced echelon form. So first of all, if the last column of the augmented matrix in row-reduced echelon form has a leading entry, then there are no solutions because you've got an equation of the form 0 is equal to 1. Otherwise, the variables whose column has no leading entry can be freely chosen. And we have a word for those variables. Those variables are called free parameters. So let's label this. Once you've chosen values for your free parameters, the other variables are then uniquely determined by these choices. So the other variables are the variables whose columns contain leading entries.